inductor, yes. So we sometimes call it a solenoid depending on the context, but generally in a circuit, if you got like a nice little coil of wire, call it an inductor. What is the symbol for inductance? L, yes, L for inductance, because it makes so much sense. All you have to do is know a whole bunch of history. But we're pretty much done with I, because I is current, and that sort of changes everything. Just as a fun fact, when you have to do phase and things in electrical engineering, you use imaginary numbers, right? So imaginary numbers, what symbol do we use for imaginary numbers? Little I. In electrical engineering, what symbol do they use for imaginary numbers? They use a little J. You know why?
Because engineers are awesome.
Well, I mean, it's actually a very practical reason. It's frustrating, but it's a very practical reason. I is current. Guess who cares a lot about current? Electrical engineers. It comes up a lot. So they have to use something else for imaginary numbers because that comes up less. So obviously it's easier to change that than your symbol for current. So yeah, this is just to show you that there are sometimes good reasons for changing variables and symbols. Not always though. Sometimes it's just named after some dude. And you have to just know that. So it's just like in you know how like this is a very big aside. In gymnastics, tricks are named after the person who did them first.
Yep.
Yeah, that's sort of like what we do in physics. You're like, you did it first. Now this unit is a Henry. It's fun because yeah, I'm just waiting for like units of Steve. You know? Millisteves. Okay, so let's talk about inductors, which are coils of wire. Now remember, if you have a current going through, and if we have a lowercase I, what kind of current is that? That's the instantaneous current. That is a current at a particular time. What do you expect that current to do as time goes on? Change. It goes up and down usually. So this is an inductor. Here's the voltage across an inductor. And remember, this comes from the definition of inductance. Okay? So the voltage across an inductor is L, which is what? Inductance. Yeah, inductance. And this is the derivative of current with respect to time. Okay? So derivative of current with respect to time. Just like, so if we have a voltage source that's like epsilon, so the EMF voltage is equal to maximum voltage cosine omega t, okay? You can expect the voltage across this thing, no matter how you have it set up, right, to be some maximum voltage cosine omega t. So this is the instantaneous voltage of the inductor. All right, so we're going to write that down. So we have VL. Actually, we'll write it as a squiggly V. All right, we also know that VL, right, going back, this is going to be VL is L d-I-d-t. Okay, so we know we have a relationship where we have VL is L d-I-L dt. So notice for all of these circuit elements, we can tell which current we're talking about and which voltage we're talking about because of the subscript, okay? If it's the source voltage, what does it look like? A squiggly E is equal to E naught cosine omega t. Right? So here's our thing. Just like with capacitance, we found the voltage across the capacitor, and we also found the current across the capacitor. For the resistor, we found the voltage across the resistor, the current across the resistor. Now, in a resistor, we don't have a phase difference. In a capacitor, we had a phase difference. What was it? 90 degrees in which direction? Which thing came first? Current. So current would peak, and then voltage would peak right after, in about pi over 2 or 90 degrees phase difference. Okay? So now, we're going to look at what happens with the inductor. We want to know the relationship between current and voltage for the inductor. Okay? So if you see this, how do we find current? What do we need to do to get current? up with di dt with this, and we have that's going to give us VL over inductance cosine omega t. So we pull this over, becomes DIL, this is dt, and you integrate both sides. Okay? So you end up with I sub L is VL over L, right? And then you get, what's the integral of cosine omega t? Sine. It's positive sine this time, right? Last time I took the derivative of cosine, you get negative sine, and you take the integral, you get positive sine omega t. There's also a, if you change the rule, omega ends up somewhere where it's a constant, but where? The front, numerator, denominator. So, yeah. Okay. So maybe get something like this.
No, it's a denominator.
Alright, so we get something that looks like this, and of course, we're trying to compare it to this, so we need to switch this back to cosine. How are sine and cosine related? 90 degrees, but in this case, are we adding 90 degrees or subtracting 90 degrees? Before we had negative signs, so you can assume this is going to go the other way. So this whole thing just becomes big I sub L. So we get I sub L cosine omega t minus pi over 2 instead of plus. Okay? So now, here's current. Here's voltage. Okay? When we look at the phase difference, it's switched. So if this is our voltage, you can see voltage now peaks just before current. Okay? And you go again, and voltage peaks, and you can imagine current peaks right here. So before, we had current peaking before voltage. Now we have voltage peaking before current. Okay? And so we say that the current lags behind the voltage here. Before, the current led the voltage. So we said current leads voltage. Now current lags voltage. And remember, we're looking for the small angle, because obviously when you look at this phase difference, okay, when we look at the phasors, here's our voltage phasor, here's our current phasor, because this is omega t, and this is omega t minus pi over 2. Okay? So this gives us still a 90-degree phase difference, but we're reversed. Okay, so capacitors behave in just the opposite way of inductors. All right? So the current lags behind the voltage. And that will make this a very easy question, hopefully. Okay.
Yeah.
Please discuss it. We'll vote again.
Is it lag? Better.
Much better. Okay, so it lags behind the voltage. Okay, you're just looking at. Remember, which way does this rotate? Counterclockwise. Okay, so that means voltage always comes before current, which means current is lagging. Okay. Thing you want to notice here. This is equal to this. So we have this I through the inductor is equal to VL divided by omega times L. Remember, what does this look like? Ohm's law, which would be V is equal to omega L I. So which of these things is R? Omega L acts like R. So this would be what? Yes.
What's the sub? Is that supposed to be the subscript next to the V?
Yeah, it's an L. It's the subscript L means the voltage across the inductor, the current through the inductor. What would omega L be called here?
Resistance?
Yeah.
X sub L, okay? So that means we now have a way of seeing how an inductor acts like a resistor. That is the inductive reactance. And what would you say about the inductive reactance here? How does reactance relate to the frequency? As you increase the frequency, what happens to the reactance?
It gets bigger.
It gets bigger. And what would be the mathematical relationship here?
Proportionality.
Proportional, linear, yeah? Okay, so it looks something like this. So this is our inductive reactance. As frequency goes up, the resistance goes up, okay? So why do you think that is? Think about what an inductor does. What makes an inductor react?
Current.
Not just current. If you have a constant current, what's your inductive what's your induction doing?
Changing current.
Changing current, okay? And how fast the current changes is how much inductance, how much induced field you get, right? Remember when we did that inductance lab? So if you move the magnet faster, you get a bigger pop on the current, okay? So what that means is, when is current changing quickly? When the frequency is high, okay? When it's moving a lot, when it changes quickly, right? That's the definition of high frequency, is you have a fast change in your current and voltage, okay? So whenever, this should make some sense with what we already know about inductors. When current changes slowly, that's like more like having a constant current, which isn't going to cause the inductor to do anything. Because remember, when current is constant, what does an inductor do? Nothing. Yeah, it acts as just a wire, okay? It has no resistance, it gives you no boost, no resistance, nothing, okay? When current changes quickly, it does a lot. So the faster you change your current, the more this thing's going to resist what's happening with the circuit, okay? Because the whole job of the inductor, right, is to resist what's happening. So if you're increasing your current, it tries to send it back the other way. If you're decreasing the current, it tries to boost it. So it resists what you're doing. And the faster you change the current, the stronger that response is. Okay? So that's your inductive reactance. And once again, you can use this version of Ohm's law for just the peak values. Now, the capital letters represent peak values. This is maximum voltage across the inductor, maximum current through the inductor, and then this is the inductive reactance, which depends on omega. Okay? All right, so let's try a problem where we use this. Remember, that's microhenries. All right, so let's talk. The first part of this problem is relatively straightforward. It's just plugging stuff in. So we have this system where we just have a voltage source and we have an inductor, okay? And we know that the inductor is a 25 microhenry, so that's L. 25 microhenry inductor, okay? We know its frequency, which is F, is 100 kilohertz, okay? And the current through the inductor reaches a peak value of 20 milliamps at 5 microseconds. So we know the peak current is 20 milliamps, and we know this happens at, 5 microseconds, okay? Which won't be important until the second part of the problem. But we want to know the peak inductor voltage, and then we want to know when that happens. So we have this Ohm's law, which is V peak, right, is equal to I peak times reactance, inductive reactance. In this case, right, so inductive reactance is X sub L. In this case, X sub L is omega L. So this part of the problem is just plugging in numbers. We have 20 times 10 to the negative 3 amps. Our frequency is 100 times 10 to the 3 hertz, and our inductance is 25 times 10 to the negative 6 henries. Okay, you plug all this stuff in, and what do you get? Yeah, about 340.
Do I need 2 pi in there?
Oh, yeah, you do. You should definitely have a 2 pi in here. Okay, good catch. Remember, frequency and angular frequency are different. Okay, yeah, because we want omega, which is 2 pi times frequency. Okay, so this gives you 0.314 volts, or you could write this as 314 millivolts. Okay, that's pretty straightforward. But remember, we know that this is a sine wave. Okay, so if you start with a voltage that goes like this, what do we know about the relationship between the voltage, so this is voltage, and the current? The current lags behind the voltage, which means it's going to start here, and it'll peak, it's terrible. It'll peak like that. Okay, so it peaks. Sorry, that is a terrible drawing. And this is why we use phase diagrams. Okay, so it's going to peak after the voltage, so it lags behind the voltage. So if you have a voltage peak here, then you have a current peak here. Voltage peak here, right? Current peak here. So if this current peaks at 5, when does the voltage peak? Should be greater than or less than 5 microseconds? Should be less than, okay? But how much less than?
Not that much.
It's not that much. The phase difference is pi over 2, okay? But that's in an angle. How do we relate that back to time? Remember, this has to be mapped to a circle. So if your period, you figure out your period, what percentage of the period is pi over 2? So what's the angle you go through to go through a whole period? 2 pi, okay? So if you have pi over 2, that is 1/4 of 2 pi. That's how you go back and forth between phase and time, okay? So phase, pi over 2, right? Because if you draw this in phase space, this is our unit circle, okay? So this is 0 to pi. This is pi over 2. This is pi. This is 3 pi over 2, okay? If you know that this is the phase difference between your voltage and your current, that means this is equal to 1/4 of the period. All right? It's just pi over 2 divided by 2 pi. So, what's the period?
1 over frequency.
Yeah, it's 1 over the frequency. And we know the frequency.
Yes.
That's going to be 1 over 100 times 10 to the 3rd hertz, which gives us 10 microseconds, yeah? So 10 microseconds. Okay, 10 microseconds is the distance between this and, so this is not drawn to scale, but you know what I mean, okay? So between peak and peak, this is 10 microseconds, all right? So when does the other thing peak? When does the voltage peak? We know it's before 5 microseconds. How much before? A quarter of 10, right? So what's 1/4 of the period? That would be 2.5 microseconds, okay? So the phase shift of pi over 2 means that this thing happens at 2.5 microseconds because it's 5 microseconds minus a quarter of the period, okay? If this were a capacitor, When would the voltage peak? 7.5, right? Because you would add 2.5 to 5 microseconds. And this graph is drawn badly because obviously this isn't 0, okay? But you get the general idea. So, for instance, when does the current peak again? So if your current peaks at 5 microseconds, when does it peak again?
3, 5, 15.
A whole period later, so 15 microseconds. Okay, so you'll have peaks at 5, 15, when's the next one? 25, 35, 45, because your current's going to peak at every period. Okay? A whole period is when you get back to the same value. If your voltage peaks at 2.5 microseconds, when's the next voltage peak? That would be 12.5 microseconds, and then 22.5, and then 32.5. Okay? So when we say that in phase space with phasors, that the current and the voltage are shifted by 90 degrees, that also can be translated to time once you know the period. Okay? All right. Any questions about that? Yes?
I have a question on the phase change.
Uh-huh.
Are we always going to use pi over 2, or will it ever go to pi?
Well, if it's an inductor, what's the phase difference? I mean, we derive this for all inductors, okay? So that means anytime you're dealing with an inductor, the phase difference is minus pi over 2. What was it for a capacitor? Plus pi over 2. So for all capacitors, you're dealing with pi over 2. For all inductors, you're dealing with negative pi over 2. For all resistors, it's what? Your resistors have a phase difference. What did the graphs look like? They were the same, right? They peaked at the same time. So that has a phase difference of 0. So for these circuit elements that we're dealing with, okay, the phase shift is always plus or minus pi over 2. That's not just random. That's something we actually derived. So we know anytime we have an inductor, you're going to be pi over 2 in one direction. Anytime you have a capacitor, it's pi over 2 in the other direction. Now when it gets tricky is if you have a circuit with an inductor and a capacitor, and then you have to figure out, depending on how the circuit's set up, whether it's series, whether it's parallel, what the phase shift is for the whole circuit. Okay, because that depends on which thing you're measuring and a lot of other factors. And we're going to talk about that, at least for the series RLC circuit, next. Okay, but yeah, if it's just an inductor, it's always going to be minus pi over 2. All right. So what we've come up with here is universal. Anytime you put an inductor in an AC circuit, you're going to get this phase shift. Anytime you put a capacitor in an AC circuit, you get the opposite phase shift. All right. And anytime you put a resistor in an AC circuit, resistors don't have phase shifts, so you don't have to worry about that. Yes.
Is that just for perfect circumstances, or is that always?
Yeah, this is all it is. Yeah. And you can look. We can do this today. We can look at this on an oscilloscope. You can actually see it and measure the phase difference between your two signals. So this isn't like just an abstract thing. This is something you can see when you build circuits. Okay. All right. Let's take a break and then we'll talk about RLC circuits.